Bart, how are you doing?
Very good. How about you, Charles?
Excellent, man. So I just recently saw your talk. Of course, we got you to come to PDC. Great talk, by the way.
Thank you.
Link to everything.
Yep.
And so based on link to everything, you've done link to Z3.
Yep, exactly.
And Niners have learned at least what Z3 is. It's a theorem prover, the world's fastest theorem prover.
Yep.
So I wanted to come and talk to you about what Magical Bart has done.
Okay.
So what's going on?
Sure. Maybe we should start by talking a little bit about what link really is, right?
Okay.
There are like different, there I use the word, dimensions to it. Like historically, like lots of people have been querying persistent data. Like you're doing link to objects or a list of T. Yeah. Or you're doing link to SQL or entity framework to, say, a relational database that contains a lot of information. And so there we're talking about data that's persisted and at that particular point in time when you're actually launching the query exists in memory somewhere or exists on a disk. Now what we added after that was things like, for example, Rx, where you have a time component. Like you have data that doesn't really exist at the point that you're formulating the query, more at the point that you're subscribing to the query. Like, for example, mouse moves. Well, we're talking about mouse moves that will happen in the future. And when the mouse move happens, it's pushed through the pipeline and we do filters and all of that stuff. Turns out that there are other ways that data can come into existence. Like, for example, link to objects. You can have an iterator that when you call move next, it's actually doing a computation to get like a prime number. Next prime number might take a long time to do so. So you have this time component, you have this lazy component, you have a potential of persistent data. But there's actually a fourth one, where you're talking about data that doesn't exist at all. Data that you can't even enumerate. And that's where actually theorem provers come in. Like you're saying something like, imagine you have the space of two real numbers, which you could see as, a two-dimensional space, right? Or three numbers, and you have a cube of numbers. And now you want to pick some number in there, or a triplet of numbers, such that certain constraints hold. Well, the way to do that is not to enumerate like all the real numbers. It's even not possible to enumerate all the real numbers. You can enumerate all the natural numbers, but it will still be like just a not done to find like just some number that actually holds particular constraints. So for things like optimization problems, you're talking about data that doesn't exist. You're saying like, what if there is like three numbers, such and such those constraints hold? And then you basically say .solve, and the theorem prover is not going to enumerate all possible combinations. It's going to apply mathematical transformations to find, something for which a particular set of constraints holds. And that's what things like Z3 do. Those are theorem solvers. And so the official name of that is SMT, Satisfiability Modulo Theories. Now, the thing, or theories better. The thing that we need to explain there, of course, is like, what's satisfiability? Now, everyone knows propositional logic, like,
Yeah, everybody knows propositional logic.
I guess so, like people are working with Booleans in C# all the time, so people should know that.
But they may not know that's
Exactly. Yes. So let's actually define it maybe a little bit.
Sure.
So if you have a formula like, X and Y with double n%, you really have two Booleans here, Boolean expressions, Boolean valued expression. That might even be, name starts with B. That's also a Boolean expression. Now, for example, if you have something like name starts with B and name starts with C, it might be a reasonable question to ask, can this thing ever evaluate to 2? Which means, can you find a name such that that predicate evaluates to 2? Well, I can't find a name unless I don't know anything about Unicode, for which, it both starts with a B and a C at the same time.
Yep.
So that formula is not satisfiable. You don't have any set of inputs to that formula, like bindings with the three variables, that makes the formula evaluate to 2. And so that question of, can you find some inputs for which a formula holds true, is called satisfiability. And that's what things like SMTs do, like Z3.
Okay.
Now, comes actually useful in a lot of cases, like, for example, VEX, program exploration, generation of test cases uses Z3. Well, why does it do so? Well, let's just go conceptually here a little bit, or not into too much details, but the idea is like, if you want to generate test cases, for some complex logic where you have lots of branches, you might want to say, well, hey, this basic block that I have sitting here in the middle of a while loop instead inside of a for loop, inside of an if else, I want to hit that code path. How do I get there? And so the answer is, well, you formulate some theorem. A theorem that says, like, what if the evaluation of the while is true, such that we're inside the body of the while? What if the for loops condition is true? What if the if is actually not true, so that we're in the else case? You basically formulate all of those constraints, like, the loop variable needs to be lower than 10, otherwise I won't be inside that block. And you continually finding, and then you say to C3, well, in order to get to that block, those 15 constraints need to be true. Please find me whether this is satisfied. And if the thing says no, it's not satisfiable, we've just found that code. It's code that can never be hit because there's no set of inputs that causes all the predicates to be true, so we can't end up in that block. Or you find some inputs, which might be total nonsense, give 42 to the age and like some name over there and that, and ultimately we end up in that block. Well, at least you have found some inputs that cause you to get into that block. And so that's like what things do to find like program analysis and find, basic block analysis to find a place where you hit that particular code path. And there are lots of other things as well, like maybe another example is spec sharp.
Sure.
Where you basically say like, hey, I want to have the constraint here that the input is not null. Well, now actually, when you write some call to that method that has something that shouldn't be null as the input, you basically formulating constraints. Like when you're doing the type checking for the call side, you actually have a set of constraints based on, all the things that the parameters need to obey to, and then it will say yes or no. Like, can your code ever violate those constraints? Meaning that if it's ever possible for the input to be null, we should reject this program because, the thing that you're calling cannot handle null. And you can go much further there. Like, for example, prefast and prefix, which are static analysis tools for C and C++. They do exactly the same kind of things. They say, well, if you call the copy function, memory copy from an array with a length and an index and all of that stuff, well, you're better not passing in an array that's smaller than the index that you're going to copy from, because then you're in somebody else's memory. So actually proving that your program can never have those inputs is actually something that SMTs can do. You basically give all the constraints and it says, yes, this is satisfiable. If you do such and such, you will actually end up corrupting memory. And on a much larger scale, it has also been used for things like Hyper-V checking, like, making sure Hyper-V is secure. You want to have some theorems that are unsatisfied. The theorem that says like that one guest OS can violate the contract of another guest OS. You formulate that gigantic thing and then it says, well, this is unsatisfiable. There's no set of inputs that can ever cause memory corruption in somebody else's memory. So that's what you need, those kind of.
So let's talk a little bit about it. I mean, so Z3, it's a general purpose theorem prover. So these theorems, the way that you implement them are mathematical formulas or what? What are they? What's the structure of the theorem?
Okay, so like the structure of a theorem is basically, let's just go to one special set of them. It's something like you say you have some model over integers, for example. You say like x is an integer and y is an integer. And then the constraints, which for the theorem is actually something like x is larger than 0 and y is larger than x. Please find me what is something such that this holds. And then you can say, yeah, sure. If x is 1 and y is 2, I have something that holds here. But equally well, C3 could say, well, if x is 1 million and y is 1,000,002, it will say that's also something that satisfies the formula. So it's not so much about enumerating all of the results. It's more about, can this ever be true, yes or no? That's basically the output of the theorem filter. It's like yes or no. If it's unsatisfiable, the output will also contain a proof that says like why it's unsatisfiable. And when it's actually satisfiable, it will give you what's called a model, which is basically a binding of all the variables, like in this case x and y, to values that make it evaluated true. So then you have your evidence that it can actually be done. Like, if you do x is 1000 and y is 1001, sure, this thing evaluates to true. So you can always check that. Now there are also other tools that do pretty similar things. Like there's like some tensions here with something called Solver Foundation. don't know whether miners have heard about that one, but it's something that the technical computing team has been doing with Microsoft here. They have an additional dimension to it, in a sense that you have a set of constraints, but you also add to that an optimization problem. You're saying like, I want to minimize the price to get the maximum amount of oil that has certain characteristics. And you formulate all of those characteristics with different places you can buy the oil from in terms of a theorem. Like you're basically saying, well, hey, for my production plant, I need 2,000 barrels of oil. And then you say, well, I can purchase oil from Venezuela and Saudi Arabia. And then you say, well, the transportation costs for those are different. The characteristics of the oil are different. Like in the Saudi Arabia oil, I can use 80% for the production plant, while in Venezuela, only 70% of the oil is usable for my purchases or vice versa. So you feed all of those things in, and then you say, dear solver foundation, what's the most efficient allocation of the number of barrels from this location and that location, such that I actually have minimum cost, but maximum throughput. So in that particular case, you basically have an optimization problem, which is also a set about constraints, but it also has a way to say, I want to minimize this or maximize that.
So that sounds like, algorithms.
Exactly.
Exactly what an algorithm is.
Yes. It's like, it's a very declarative way of saying what you want.
Yes.
So that's a very important distinction here. Like in a typical algorithm, you would actually be doing loops and all of that stuff. Well, it's not a necessity to do it that way, but like people all of a sudden think about imperative style code there. Now, in this case, it's like an optimization problem, but you don't have to write any code for it. You basically say, those are my constraints.
Yeah.
And again, you're talking about, well, physical data, right? Because if you would be doing that in terms of, say, enumerables, like, what if I allocate 1 barrel of oil here and 1,999 over there? That's like a valid combination because it needs to sum up to 2,000. Let's compute all of that stuff and stick it in some list, a sorted list, and then order by in the prices. And then do it for 2, 1,998, 3, and so on. So, like, doing that kind of computation it's very expensive. It's not the kind of way that you want to go about solving it. So those things like Solver Foundation and Z3 allow you to stay on a much higher level, saying what you want, and they figured out how they can solve it. Whether it's using linear algebra or some other theory, which is where the T in SMT comes from, Satisfiability Modulo Theories, and they find out how to do it. So if you look at Solver Foundation, there's even a plugin model there, like people can plug in, their own solver engines that know about certain domain-specific things. And like here we're talking about, linear algebra and natural numbers and mainly real numbers, but they have much other things. Let's actually give another example.
Sure.
If you talk about C3, C3 also knows about functions. So you can say like, is it ever possible to have a function f, which takes in a single argument, and a function g, which takes in 2 arguments, such that f of x and g of x, 0, so g applied to x and 0 applying those two things, is always the same. So basically you're now asking, like, can you find a function such that when I give it anything, and another function when it gives anything, then the two results are the same. Like, so here now you're talking higher order, and you're talking about, please find me a function. And so what C3 does, it comes up with total functions. It says, sure, if you have a function f, when it takes in 0, it returns 0. When it takes in 1, it returns 42. When it takes in something else, it returns 99. I've just come here for something.
Sure.
And then you have a function g. If you take in this, it returns that. And if it takes in that, it returns that. Well, if you have those two functions and you implement them somehow, sure, you have something for which that particular theorem holds. And so here you get in universal quantification. Now we have another level, another level of expressiveness here. That's actually the all keyword or the any keyword, the link. So you say something like, for all x, is there something such that this predicate holds? And people have been writing that in LINQ all the time here. They say something products.all, where product goes to product of price is larger than 0 to find out that there is no single product that costs 0 money, because you shouldn't have that in your shop. And so that's kind of the thing that you're doing there. Sure, that's the same kind of predicate logic that you're using here. You're saying, for every potential x, can I find something such that this particular logical formula actually holds.
Excellent. Now, this is a good, outstanding introduction. So let's now talk about, I think it's clear to everybody now about certainly what LINQ is, and certainly now what Z3 is, of course, the general purpose theorem proof. Now, you connected the dots between the two. So the first question I'll ask you before we get into the how is why? Why did you decide to do
Okay.
Besides,
Yes.
let's do LINQ to everything.
Exactly. Yeah. That's like, for its own interest. It's an interesting thing as well.
LINQ to work.
Exactly. Simpson, yes, I don't have the Bart Simpson here, but we showed it.
Yes, we have.
Yeah. So why did I choose to do this? Well, first of all, it's kind of interesting, as I explained before, that LINQ has many phases. So the phase of talking about non-material data is something totally new. Like, you're talking about, the desert of points, and you need to find a single point for which a certain constraint holds. Like, that's kind of linked to the unimaginable, I call it. Or imaginary, like if you have complex numbers, remember and access.
Yeah.
Now, traditionally, formulating those things, for example, in Solver Foundation, has taken domain-specific languages. Like in case of Solver Foundation, it's called OML. It's like some language that's like, lots of brackets and, like lots of parentheses. It's always like Lisp. And you have to write your theorems in there. And you don't have anything like, type checking. You don't have the familiar IntelliSense of an IDE. You're basically just writing some text. And apparently, there are business analysts that know how to write this kind of stuff. But if you want to integrate that in general purpose languages, it doesn't quite fly. You just have like some huge string that you're giving to the Solver Foundation engine, or you have to do lots of imperative code where you say like, Solver Foundation, I want to have some variable A, which is of type int. And then you say, declare some variable B of type int. And you're in that imperative land, you're saying like, something of that type, something of that type, and then you're formulating constraints. And they've made it kind of easy using lots of operator overloading. So you can sort of write, x is larger than 5 and all of that stuff. But it's still a lot of work. Now it turns out that in LINQ, we already have something to express constraints. It's called the wave keywords. Like, if you say, for hypothetical data in this search space, where those constraints hold, please select me a solution. You basically use the LINQ query, that kind of syntax, to express exactly what you want. And you can do exactly the same, of course, with C3. I've given a sample here now of Solver Foundation. And Solver Foundation is one additional dimension where you actually do the minimization or maximization of something because you want to do optimization, right? So there you can write something like, from the number of barrels of oil that I get from Venezuela and the number of barrels of oil I get from Saudi Arabia. Those are my constraints using wave keywords, where, the oil over there costs that money, and I want to get in total, like, N times, Venezuela times its price plus, Saudi Arabia times its price needs to be lower than that because I want not to spend more money. Like, you feed all of that stuff in, and at the end you say, well, I want to optimize something. But what's optimization? Optimization is like, virtually, if you could enumerate all the solutions, which might be millions and millions of solutions, possible allocations, conceptually, you're just sorting them. You're saying, like, I want to get the one for which some maximum value holds or some minimum value. We already have that in LINQ. It's called ORMY. So basically, why don't we use that syntax to express our constraint problems? And that's where LINQ to Z3 and LINQ to Solver Foundation sort of come in. Exactly that.
Amazing. So your implementation of this, last time we talked about how you do your LINQ to everything was with Eric, remember? We interviewed you because 2 years ago now.
I guess it's something along that, yes. Was the 100th episode of Facts for...
Yes, it was.
Yes.
And it was the perfect 100th episode.
Okay, thank you.
This actually might be the 200th, by the way.
Okay, let's see.
I'm not sure when it could very well be. So I can see clearly the connection between, LINQ itself and theorem proving. In terms of constraints, as you could say. So now we're now thinking about LINQ in a different way.
Exactly.
So that it now fits in nicely in the Solver Foundation.
Yes. So it's actually the LINQ part. Let me point that out. LINQ is language integrated and it's great. It's sort of query as well, but not a traditional kind of query.
LINQ.
Yes, it's kind of LIN, you know, and I could use the M word. Let's not do it. But
Why not?
well, you know, I could.
Language integrated language. Say it.
Language integrated monads.
Yes.
Yes, that's what it is.
But I want to let's talk about that for a second.
Yep.
Because look, I want to be honest.
Actually, we should start with our account here. But
We should do what?
do some drawing on the whiteboard.
Yes, absolutely. I mean, we need to get you up there. But I think just for a little random tangent, which is fine. This is channel 9.
Yep.
So let's talk a little bit about monad.
Yep.
In some sense, LINQ is a monad.
Yes.
Right? I mean, that's how it's implemented. That's how you got it implemented.
Exactly.
That's how you got it in the language.
Okay.
Now, the first question I would ask, we don't have to go through the rabbit hole of what is a monad. I think most people must start to understand what it is.
Yeah.
But I want to hear Bart De Smet's 30-second answer.
Okay.
Okay. What is a monad?
I would say it's applying some aspect to computation. So what does that mean? That means that you're lifting yourself in some different work. Let's go very metal here. Like you started with a T, something of type T. And now all of a sudden you project yourself in monads of T. And then every computation you do is subject to certain laws. Like for example, in case of enumerable, it's like about iteration. In case of observable, it's about pushing things through a pipeline. And all of that stuff can even be lazy. You know, like at the point that you do a subscribe or you do get enumerated, say, that's point that whole thing starts sticking. So that's, you know, where you come up with lazy pipelines. And if you look actually on Wikipedia and you look at monads, you know, they use the word pipeline like 10 times in their description. Well, LINQ is a pipeline. It's a pipeline of data flowing to operators. It's like same in PowerShell. You know, PowerShell was called monad at some point. Turns out for a different reason, because Jeffrey Silver like it's, you know, some philosophical stuff that's actually also, you know, about monads and things. It happens that actually PowerShell itself could be seen as a monad because it's a data processing pipeline. We've actually adapted an observable at some point, so it's exactly that.
Yes.
So if you actually watch my session or link to anything, I start with the node or the maybe monad, where you basically want to compose things. You want to say like, I have a value and I want to call a function on that. And I only want to call the function if the value is not null. Like having that logic of checking for null and conditionally applying the function or forwarding the null. Like if it's null, it stays in, it's null propagation. But if the input is not null, I want to call the function. All of that logic can hide inside the monad, meaning that you will never call the function if the input is null. So that's the aspect of the computation that you're sort of hiding in the monad. It's a level of abstraction. And now you can feed any data to that monad. You can give it null, and then null will come out. It will never call a function or calls a null reference exception. Or you feed in Bart. And for example, you're doing the monad that uses to up or to transform input. Well, then Bart is not null, so it will return Bart in capital letters. So that's what the monad does in that case. It protects against null. So that's just one sample of such a thing. But it's about having computation or an aspect of something hidden behind it. Like, you know, it's monad of T. It's no longer the naked T. It's like something with additional stuff around it.
And so just to extend a little bit on that, in my sort of generic understanding of this, it's that essence of what you just said that makes a monad the perfect unit for composition.
Yes.
We want to build a composable system.
Exactly.
Which is so important for software.
Yes, exactly.
So forget about the term monad and just think about...
Yes, it's compositional at a higher level.
Yeah.
That's what it is. Yeah.
Right on.
It's like, you know, people like to think about, you know, component-based architectures, and where you have puzzle blocks and Lego blocks and build them together and you get some bigger construction and it's still composable. Well, doing that same thing in a functional setting, where you basically are calling functions and you're composing them, subject to some things like node checking. That's where monads comes in. And actually, if you go all the way back to Ryan Beckman's video on monads, he shows actually that composition, regular function composition, and this operator called select menu have sort of the same signature. Just a couple of things are swapped around a little bit, but if you morph it a little bit, you come exactly with the same thing as function composition. And so that's really what it is.
Excellent.
Yep.
Now, Thank you. So let's dig into how you implemented this and how we would use it.
Yep. Let's maybe
Rock and roll.
Yes,
We get far to the whiteboard, which is a necessary ingredient.
exactly. So actually, let's start with talking about the way you formulate a theorem. Okay. So the way you do that is by starting with a theorem of T. And so this theorem of T type is a theorem expressed over some domain, I will call it T.
Okay.
And the domain T that could contain lots of variables. It could contain an x of type int, a y of type int, and maybe a function that takes two ints and produces an int. Like those are the things I want to formulate constraints of. So how do you formulate constraints? Let's first draw some conceptual diagram here. You start with a theorem of T. And here you see that monad kind of thing again, right?
Yeah.
So you have this theorem of T, which is not just a T. It's slightly more than just a T. Now, what you're going to do is, given this theorem of T object, you're basically going to add constraints to it. And the important thing here is that it's a loop. You're doing a where clause that ends up in a new theorem of T. So you're basically adding some constraint. Let's make it concrete now, right?
Yes.
Say that you have a theorem where x is an anonymous type that contains an x, and I will actually type it as follows. I will do default of int, which is a little bit as if you're saying x needs to be an int, but I'm doing an anonymous type here. I don't want to go somewhere else and create a nominal type that has an x inside it.
Okay.
I just want to write, this thing in mind. And I will show where it comes in later, how you actually do it concretely in C#, how you create a new theorem of T with such an anonymous guy. And say you have a y, which is also a default of int. Okay. So in reality, those two things are evaluating to zeros, of course. But we don't care about that. We just have some prototype, of our search space. It's really as if you're doing something in mathematics. You would write something along the following lines. You would say, x is a natural number. Y is a natural number. Actually, then I should use uint. But okay, sure. I should write C here, for numbers. In reality, this search space is like the Cartesian cross product between the two. Like, you're searching for on, some plane, a two-dimensional plane of natural numbers. You're searching for an x and y such that certain constraints will hold. Okay? So I want to pick one for which constraints holds. Okay? So now, if you do where over here, you can do something like, for example, where x is larger than 0, where y is larger than x. Okay. And so I'm doing two where calls here, but the first where call is actually do it twice. You have a theorem of T which doesn't have any constraints yet. I'm doing where x is larger than 0, so my constraint set now contains x is larger than 0. In reality, I have a new instance of theorem of T. Like, I'm not going to draw all the instances I'm creating here. They do another where call, and that other where call says, y needs to be larger than x. Well, you basically add that to this constraint set, y is larger than x. And you continue doing that. At the end, you of course want to get something out of this.
Yes.
You want to get out whether or not this thing is satisfiable. And so that's where you want to exit the monad. And actually take this thing back to LINQ. At LINQ you have an enumerable of T. You do a where, you get a new enumerable of T. You say iterators and link to objects. You do another where, you get another enumerable of T. Same thing for iObservable, same thing for iQueryable. You stay in that world. You don't fall off the cliff. Okay? Now, as soon as you want to get out, what do you do in case of LINQ? You do for each. Or in case of Rx, you do subscribe.
Okay.
Now, or you can do await. In C# 5.0, you can await an observable. That's also
Yeah, just
get
get out.
C# 5.0. I'm kidding. Oh, I see. Yeah, sure. Somewhere in the future.
Yes, there you go.
So you do this kind of way of thing on enumerables or observables, and what you get out is, T's, right? Enumerable of T becomes T's through the means of for each or on next calls or whatever. In this world, it's different. we're not going to enumerate all the X and Y combinations for which this holds. You simply want to get, some sample of this. Like, is it possible to satisfy those constraints? And Z3 might say, sure, if you make X equal to 1 and Y equal to 2, this thing holds. Equally well, it could come up with something like, X is 42 and Y is 9,999. Sure, that's a sample for which it holds. But it's not going to give you all of those. It's just going to give you one. Or it's going to say this is unsatisfiable. I can't prove this to you. And so it's not about iteration to get stuff out. The way you get things out in this world is by doing solve. So solve is the get enumerator or the subscribe from the other world.
Okay.
The only difference is that you don't get back some object like enumerator of T or something like observer of T that you're feeding in. What you're getting back here is a single T or null. Null if it's unsatisfiable and T if it was satisfiable. Now, of course, this question mark could be encoded differently. It could be that you throw an exception if it's unsatisfiable, like new Theorem unsatisfiable exception or whatever. It depends when you want to get it as data or something else. Could even have like some continuation kind of thing here, where the solve actually takes into functions, a function on success and a function on error. And on success, we will actually give you the T. Like, sure, I found an example, X is 1 and Y is 2. Here's your T, like I've proven that you can do it. Or it could tell you, I can't find anything. And then you can take some other actions. And so what you basically have here is sort of the same as enumerable. You stay in the world till the point that you want to get the results out. In this case, it's 1 or 0 results. Like it's really, 0 or 1. Versus, in LINQ, it's typically, any number, right? It can be 0 elements, 1 element, infinite elements. In this world, it's just 0 or 1. Okay. And so that's actually what you get. Actually, makes me think of it. You could create a weight pattern on top of that. You could do, a weighted theorem. And then, when you weight the theorem, it will say, hey, here's the results at some point, because C3 might take a long time to produce the results. And so you could actually use asynchronous programs.
So now I have one quick question, because we use the M word.
Yes.
The thing that I've learned, having been brainwashed by Eric, and then most recently Greg Meredith is doing a lecture on this, is the notion of comonad.
Yeah.
And so monads are great for putting things in.
Yes.
But you need their mathematical dual to pull them out reliably.
Mm-hmm.
And so what I wanted to ask you was, is that right there, Sol, was that a comonad?
And well, the thing is that it's just a way to get data out.
Okay.
It's not that, the way that you get data out, you start to do compositions over that, or you start to reason about that much more extensively. Here it's a single arrow.
Okay.
Like if you want to do indeed the comonad stuff, like you want to have like operators again.
Yeah.
That, work on comonads and give you, something else in the same comonad. So that's
just another rabbit hole we'll go down a little
yes
time.
Yeah, exactly.
Right on. So please continue.
Okay. And so now the way that actually this thing works, you could actually sort of stop here.
Okay.
Say like, this is the way it works.
Certainly.
The idea is that you get those constraints in expression trees. That's the only thing you need to remember here. Now, this whole thing is even non queryable. I should also point that out. The way it works is just by encoding the state machine. So you have a theorem of T, it has a wave method, and you get back a theorem of T. So that's basically it. And that means that's enough for the LINQ syntax to bind against it.
Excellent.
So let's actually write some simple query, a concrete query that actually does everything I've done here.
Perfect.
So let's wipe out some stuff and just, show how you would actually write this kind of thing in LINQ to Z3. Okay. So first you need to define your theorem over which you're going to express the constraints. Now, how do you do so? The idea is that we have something called the context, just like LINQ to SQL has a data context. And the thing is that there you can actually add a logger. It's not for change tracking because the world is all changing, like you just, it's not that you do update operations on Theorem or something. And so what you want to do here is something like using var ctx equals new Z3 context. Okay.
Okay.
And in reality, you could actually create a subtype of C3 context which has many theorems on it. So basically, if you draw the diagram here, like, a link to SQL, you actually have the data context, and the data context contains, one data context contains 0 or more tables. Okay?
Okay.
That's the relationship there. In Z3, the Z3 context contains one or more theorems. That's basically it. Theorems can actually even be composed. You can have a theorem that you formulate once, and then you create some theorem on top of that, to refine it. So you can even have, cross-table joins, like cross-theorem kind of compositions, like all of that stuff you could imagine as well. Yeah. But let's just talk about the reality. One context has multiple tables or theorems. So that's basically that idea.
Okay.
So now what do? You want to create a theorem. I haven't created the subtype of C3 context which already has a property that has some theorem or T-type. I basically want to create it on the fly. And you can do that. The thing you do here is something like var T equals context dot new theorem. But now this thing needs to return a theorem of T. That of T part is essential because that will give us intelligence on all of the type info and type checking. So how do I create a new theorem? Say, for example, with an anonymous type. Okay. I could do two things. I could say new theorem of some concrete type, but then I can't use an anonymous guy because I can't name it over here. Okay. So you could do that. You could create a class that has public property X, public property Y of type int, and then feed it in here. Okay, fair enough. Another way you can do it is that I have some types called theorem or symbols. I think I call it symbols of, and then you basically give some types here. Symbols of int, int would give something that has an x1 and an x2, which are generically typed. Today you could do that with a tuple. This was invented in 3.5, where we didn't have tuples yet, but it could be a theorem of tuple, where you basically have item 1, item 2, but it's kind of ugly because then you have to do where item 1 is larger than 5, where item 2 is larger than item 1. What does it mean? Like it lost its meaning. Okay. So the other thing you can do is basically pass in a witness or a ghost type. A ghost type is basically just something that gives you the shape of the data. And then we use that T by means of generic type inference. So basically that's what I'm going to do here. I'm going to write something like new curly brace, x equals 0, y equals 0. And in reality, I would do a little bit more typing. I would not use 0 here, but default of something. Default of int, so that you sort of see the types here. It's like you're declaring a type in place. I don't care about the fact that those things are null or 0. I just care about the shape of it. Okay. You can also have domain-specific types. Like you can, for example, int only goes to 2 power 31. Like, if you talk about linear algebra, I'm like, you won't find in ancient Greek textbooks of mathematics that, the natural numbers stop all of a sudden if you have these 32 bits, right? So you can have big integer, you can have things like, the real numbers, like with the notion that actually Z3 has, which has much more potential for precision, for example. So you can have domain-specific types here, which also have operator overloading. Like, if you have a default of natural, that natural will have a larger than operator overload, and you can just work with them naturally.
Okay.
Natural. Perfect. Sounds good. So now you have that theorem, which is in this case the theorem of T, where T is this anonymous thing. If you would hover over it in Visual Studio, you would even see something like this is a theorem of T, and then it would say where T is, and then it would actually repeat this thing. Like it would say it's an anonymous type where X is an int and Y is an int. So you would even see that, in the type then first. I need to use var here because I can't say the name of that particular piece. Okay? So now that you have that, you can do something like var. Actually, this theorem is it's the empty theorem. Like everything will hold here, right? Like every combination of X and Y is fine. Okay. And now I want to, create something else, and let me just call that thing, result or something. And now I do something like var what should I call it? S for symbols
Okay.
in T, where S dot X is larger than 0. And so what I'm getting here is when I do S dot, I get the intelligence for that T. And so now you can just write S dot X is larger than 0. And you can continue adding where clauses here, and ultimately you do select S. And then at the end, you do something like, console right line of results.solve. Okay? And what solve does is it returns you some of those things. It returns you a single value of this particular type, where X and Y will no longer be 0. They will be such that all my constraints hold. Like in this case, if I only have S.X is larger than 0, X could be anything which is larger than 0. As long as Z3 found that that's a good combination for which my theorem holds.
Okay.
In this case, I don't have specified anything over Y, so Y could be anything as well. And so then that's basically the way you write it. Now, how this guy translates, lots of people don't probably know that, but this translates into T dot where copy this thing S onto S dot X is larger than 0. And then you have all of wheres, and at the end you have select S. And because this is the identity selection, actually C# compiles it away. Like if the last thing in the query expression is select the identity, it doesn't emit the select call, for better or for worse. Like in some cases that works, in some cases it doesn't. Like it depends on the kind of query provider you're writing, whether you want to see that kind of thing. The select S doesn't go away if it's the only thing. So if you would do from S and T, nothing here select S, you would see T dot select S goes to S.
Okay.
And the reason is that, the select might transform your type. Like for example, if T is a list of ints, you don't want a query over a list of ints, even if it's just using a select to all of a sudden return a list of T.
Sure.
Because then it's mutable. And then you can pass it around and say, okay, this was a list of something. And then somebody comes in and adds a where class to it. All of a sudden your type changes to null. That's not the kind of thing you want. So if it's then only a single select, that single select actually still emits a call. But if it's something that comes at the end after other operators, it goes away.
Okay. And of course, in this case, it's the constraints and the where that matter.
Exactly. So I don't care even about selects. If it would be there, it would be fine. But I don't care.
You're proving theorems here, man.
Exactly. All right. It's even further. Theorem of T doesn't have a select method at all. So if I would put in select something non-trivial here, then it would compile. It doesn't compile. The compiler would say, I can't do this. The reason is, you're just finding an S you can always project after this. You can do like result.solve, where you get something of this thing, and then you can apply a function to transform it. Like, for example, to do the to string on that thing. Like, you don't need to do it in select. Could easily be implemented up. Now, the way this where is typed, so that where, as we have seen before, actually exists on theorem of T, right? So we have theorem of T. The way that where looks is basically, it's a method, an instance method, that returns a theorem of T. Okay? And it's called where, of course. And what it takes in is an expression of a function of T to bool. And let's call that guy F. So that's essentially what it is. It's an instance method. Like typically in LINQ, we use extension methods.
Yeah.
In this world, the compiler doesn't care. It simply does T.where.
Okay.
If there is an instance method that's, has this lambda expression assignable to its first and only argument, unless there are optional parameters, let's not go there, it will basically bind against this where. It doesn't need to be an extension method. It just happens that on LINQ, we typically use extension methods because we don't want to extend interfaces. We don't want IEnumerable of T all of a sudden to have 500 methods on it. Then everyone who implements collection time needs to do where and select and all of that stuff. It wouldn't scale. But so in this case, it's just an instance method, and that's basically what theorem of T looks like.
Okay.
And inside, the only thing it does, it captures this expression tree, and just stores it in some list. Like if I had my bubble over here, like I had theorem of t and I had something like x is larger than 0 and y is larger than x, this really is a list of those lambda expressions, which contain all the information about your constraints. And the thing that solved this, the solve method, that's kind of interesting. Typically, LINQ providers take some set of constraints, like, the wheres in LINQ to SQL, and turn them into some massive string that they send to another database, in this case, the SQL. This guy doesn't even create a string. It doesn't create a string that then Z3 needs to parse. They could do that, like Z3 has something called SMT lib, which is a language, domain-specific language, that allows to express those constraints. You could do that, and how would that look? It would actually look a little bit lispy. It would look like larger than x0, larger than y0, it's prefix notation, and then you would have something like, and of those two things, and, there's the lisp here. But you don't want to write that. Now, even the solve method doesn't generate that. It could do, and if you want to, we could do that. And instead what it does, it basically emits method calls to Z3. The only thing it does, it's hosting the Z3 engine. And it says, dear Z3, please add a constraint. And add constraint takes in parameters, it's like lambda expressions. It takes in all the bonus parameters. And then it takes in some expression representation of x is larger than 0. So it's something like you do Z3 dot larger than of some Z3 parameter, and I'm just making this thing up because in reality those things are native code wrappers. They have much more ugly names. Like you do something like make binary operator with some magic constants, and it's just. But that's what's happening. Like an expression tree of LINQ here, which is larger than x0, is actually turned into method calls that are, I can use the word, isomorphic to this tree.
Yeah.
We visit this tree, we say, make some parameter called x, make some constant with value 0, and now given those two things, we make a larger than expression, given the output of those two method calls. And so we do that, and ultimately Z3 knows everything that we've done in our query expression.
Nice.
Then you can just say, when you call the solve method, and we're already doing this in the solve method because it's totally lazy, in the solve method, ultimately you say, Z3, please run this decision protocol and try to satisfy it.
Okay, so what I'd like, my question I have now is, I think this is all very clear.
Yep.
Thank you. In terms of solve,
Any?
I mean, is it void? I mean, it has to return something, obviously.
Yep.
I mean, your console are writing it, but what does it return?
Okay, it returns a T.
Okay.
So,
Because it's theorem T.
yes, exactly.
Obviously. Okay.
So class Theorem of
Yeah,
T
yeah, yeah.
has a solve method which returns a T. And throws an exception if it's unsatisfiable, or returns a null if you would constrain T on something.
So that's what I meant, right? So
Exactly.
So we're using the theorem prover is to understand logically, in its strictest term,
Yep,
does my constraint hold?
exactly. Yes.
Tell me yes or no.
Yes. And
So why not just return true or false?
I
Or
see.
if it's
Okay.
true,
yes.
like, I mean, that would be a combinatorial. I mean, that'd be a combination type, which isn't really. We're not on this planet.
Yeah.
So let's talk about the case where it's true, and I get T back.
Yes.
What does it mean to me?
Okay. So what it means, for example, if you would create a program analysis tool using LINQ to Z3, what you may want to feed in here are the constraints to hit a certain basic block. So I explained for facts.
Yes.
Well, the thing that you want to get out there is some test case that, given certain inputs, hits that particular block. So you want to have concrete values for x and y for which you know that your theorem holds true.
Okay.
So you want some kind of witness of the theorem, like a particular thing for which it evaluates true. And so that's the reason we return a T, so that you can actually get data out. You have proof over there, like,
I see.
see, it's possible to return true from this thing. Here's how to do it. Otherwise, C3 could be implemented as something that gives up after a certain time and says, most likely it's true, but it's true. Like, no, I want to get evidence here. And that's, your T is your evidence ultimately.
But let me ask you a question. So in the case of the static analysis tools you mentioned earlier for native code, typically used for drivers.
Yeah.
In Windows, quick load especially.
Yes.
What I'd like to know is if I provide you with a constraint where the exception is what I'm really interested in, because I may have a sneaking suspicion that my beautiful pattern is flawed in some sense. I want to know exactly what it is, exactly what those code paths are, as you mentioned earlier.
Exactly.
And the exception will provide me with that information? Or would I just not? That's what I'm asking.
Depends how your theorem is formulated. Like, do you go with positive or negative logic kind of thing?
Okay.
So in case of like doing verification of a program, and you won't know can it cache based on some invalidation. Like, for example, typical sample they use for kernel drivers is like KE for kernel modes, acquired spin lock and release spin lock. You need to do that in certain, making sure that those are balanced and all of that stuff.
Yeah.
So the thing you feed into to the engine at that point is basically all the code paths that actually hit this particular acquire lock, but then try to solve the constraints such that you don't hit this release lock. And then what you want to know is like, what's the code path that we were following based on the inputs that caused us to acquire a lock without releasing it? And so basically then you get the information. Sure, it will say like, you have some huge logic here. Here you have F if X is larger than 0, for example. Just pretty simple sample. Then in this code path, all of a sudden we return, but we didn't do the release spin lock thing. Like what Z3 will tell you is like, sure, say that X is equal to 3, but X could be more complicated, of course. X could come from, some global state. Well, Z3 will tell you like, if the global state is like this, you have a repro of hitting the code path that doesn't do the release spin lock thing. And so, yes, URT contains the information about like bindings of variables and bindings of global states that cause it to satisfy the case that you don't hit the release thing. Okay. If you just want to prove correctness, often you create theorems that say like, if it's unsatisfiable, it's correct because like it's not possible to hit this particular condition. Like the constraints here are such that like you won't launch the missiles, right? Like all the constraints to launch the missile is that those 15 things happen. Like please prove to me that never in the real world those 15 things can happen. And if you find that out, well, sure, then you can actually say my program is guaranteed to be correct because there's no single set of inputs that causes this condition to evaluate to true, which is unsatisfiable.
So now in the world of meta-programming, where essentially programs are data, in some sense, you're programming programs.
Yep.
That would be really interesting to be able to dynamically verify that any number of programs that are going to result from this set of operations aren't actually going to blow things up or corrupt data or destroy the whole purpose of what I'm trying to achieve.
Yes.
Or just time out or whatever.
Yep.
Talk to me about that. That's essentially...
Yep. You could go very far with this, like, invite maybe the deniers to take this thing and take an expression tree, system link expressions, and I dropped my pen here.
No worries.
Yes. So you use system link expressions, and you just come up with an expression tree that has some control logic in it. Since .NET 4, we have statement trees, right? And instead of just doing .compile on that thing, what you do is like you do some constraint solving of all the conditions. And before you do a compile, you're actually trying to find that there are certain code paths that are in depth, for example. Well, what you could do is you could create a smart2.compile method that first rewrites the expression tree based on theorem solving of all the conditions to eliminate the bodies of code that are in depth. So that lightweight code gem doesn't need to waste its time trying to come up with verifiable IL for the things that will never execute. And so now you have this kind of method there, right? Where you have an expression tree, and then you sort of extract pieces of the expression tree, like, the if condition, the while condition, all of those guys, and you feed them to Z3 in just that form to find out whether certain places of the code can actually be hit. And so now you have this kind of very method thing where you're, generating expression trees based on analysis of other expression trees, and, our mind is too small.
It's really, really interesting. And I think it's important to point out for people this is the kind of marketing I like to do personally. That Z3 is in fact the fastest theorem prover in the world.
It has competitions. Yes.
It does. I mean, it really, people need to know that.
Exactly.
So, and that comes out of the Rise team.
Exactly. Yep.
Wolfram and his gang of geniuses. And so I want to give them a plug because in some sense, I mean, the future of C3 is very interesting.
Yes.
And
So just in the language basis. Yep.
So let's talk about that. I mean, is it used in PAX?
In PAX it's used.
It's used in obviously a lot of the other Rise projects.
Yes.
But let's think about, because you're a creative dude, and so some novel ways that Z3 could be used. I mean, for example, inside of a sort of a language interpreter or pilot.
Yep.
That's certainly something that can be done.
And like there are places where this has sort of been done. Like for example, the whole M thing that we did at some point. As we actually still, investing some time in, the modeling stuff. And in the M language, you have an interesting set of constraints that you can put in types. You can actually have a type with a where clause, where you say like, hey, I want to have natural numbers here, but they need to be larger than 18 because I'm modeling the first one. Now at that point, your types are not just names anymore. They're not just part of a tree structure or a graph structure if you have multiple inheritors, but like they're not a tree structure anymore. Just not just a tree structure. I need to put the word just in here. Like it's not that a natural derives from number. Like it also has something else. It has auxiliary data that says like, and those are the constraints to have membership. So actually a type you should think of as a set, right? You more like the type of naturals is basically the set of all the instances of naturals which are in that set. Now, at the point that you do something like naturals where the natural is larger than 5, you basically have cut out part of the set. Now, of course, then you might want to have a method that says, I want to return naturals that are larger than 10. Now, given two naturals that are larger than 5, what are the mathematical operations I can do on them to make sure that my return is larger than 10? Like at that point, you're solving constraints. Like you need to basically see the constraints of one natural or another natural, combine them somehow and say, is there no such value for which the returns constraint doesn't satisfy? And in that case, you basically have a type checker error. And so now you have rich types that actually require, theorem solving at compile time to figure out whether your program is correct. And of course, there's a dark side to that as well. The error messages you will get will likely be something like, hey, you got two naturals here, one of which is larger than that, one is larger than that, and in this place of the program, you're not adding one, and therefore it can't be larger than the sum of two or something.
Sure.
Like you will get those long things. But let me point out that actually C3, when you do the solve thing, either you get a T that says, this is the way you satisfy all of those constraints. That's fine. But if they are not satisfiable, you can actually ask C3, hey, what's the proof? And that's your error message at that point. That's the error message, like why this particular thing cannot be satisfied.
Perfect.
So you get rich info there. It might be utterly unreadable, but you have the mathematical proof there. And then it's just a matter of how you present that information. Just don't get too bombastic in like creating a type system that has lots of those constraints.
Sure.
Because the more you have, the more complicated your messages will get, of course. But that
Well, you just have a message interpreter that you write in C,
for example.
Yes. Figure out what it really means.
If it is still that's on, but
There you go. So you have sort of this nested C3.
Yep. Exactly.
Very, very mind-blowing. That is what I can say. Is there more you want to talk about?
We should show one sample maybe.
Even better.
Yep.
Let's watch you code.
Okay. Well, the code is already there.
Well, that's, it's still fun. You wrote it. That's
Here we go.
Okay.
So this is actually the thing that I showed on the whiteboard, sort of, at some point. So we have a Z3 context to which we attach a logger. And so the idea of the logger is, again, it's a text writer, just like in a link to SQL or link to SharePoint. This will basically bring the things that the Z3 engine is dealing with. It will print your theorem in the Z3 format. It will also emit like why something is satisfiable or not. So you will get some evidence on that. So here I have a theorem, which is basically creating a new theorem of symbols. So symbols is that tuple type I created before to find variables there. And the only thing that symbols is just, it's actually printed way too small.
Yes.
But so that's like what a symbol looks like. Okay, so basically, T1, T2, T3, it has some non-generic base type, but it's just properties. It's get-only properties. That's what it is. And so here I formulate some theorem over 5 of those symbols. Those symbols could have other types. You could even have a symbol that's a function type. Like you could say, is there a function from int to int which satisfies those constraints? And then you get in different theories that you need to solve that. So the way this translates into Z3 will be more complicated now. There'll be more syntax used. And so here you have d.x1, and of course I get intelligence. Here if I do dot, you see I get x1, x2 statically typed. So I can basically create all my theorem here. This is, I don't know whether I took this from documentation or it's something I just typed, just do some complicated mathematical stuff with all those variables. But you can see that I have 5 of those guys and I have 5 symbols. If you know a little bit of linear algebra, having 5 equations with 5 symbols makes it, it's the ideal number, to sort of get solutions. If you have too little, you still have degrees of freedom. If you have too much, you might actually be overspecifying the problem that is not satisfiable. So there's some chance that this actually works, and that my constraints are not too bad. But for example, I could add a constraint, of course, x1 minus x2 is also lower than 1. Well, sure, this will never hold. You can't have it such that at one time it's large, and at the other time it's actually lower than that. But so here I'm doing theorem solve, and what you see as the result type of solution is actually one of those guys. It's solution of int, and so forth. Okay. And so this thing will return solution on which I can do x1, x2, x3, x4, and x5, and basically print it out.
Nice.
If this was unsatisfiable, this would throw an exception, which is a theorem unsatisfiable exception, which contains all the Z3 outputs, containing information why it was not satisfiable.
Okay.
So let's actually execute this guy. It's building. There we go.
Nice.
That's already the next one that's running here. But here on the top, you basically see, I don't know, is that readable?
Well, it has an interesting pattern.
Yes, well, the pattern is actually from the Sudoku that comes behind it. So that's interesting. So here you basically see x1 needs to be -3, x2 needs to be -6, and so on. Then all of those 5 constraints will hold.
Okay.
And of course, you can plug those values in and see that everywhere it cross evaluates to 2. Perfect. Now here I have another one underneath, and that actually illustrates an interesting point. And here I have a Sudoku. Now, Sudoku creates a theorem, or actually a base type of theorem. It creates a theorem of Sudoku. So it's a special theorem that has domain-specific knowledge about Sudokus. And the thing is that when we create one of those guys, there's a way in LINQ to Z3 to communicate a base set of constraints. Every time I want to solve a Sudoku, I do not want to put in that all the rows need to have distinct values. I don't want to put in that all the columns have distinct values. I don't want to put in that every single cell is between 1 and 9. Those things hold for every single Sudoku. So the way you would actually do this kind of standard behavior in object-oriented database, not database, object-oriented programming, is you would have a base type that contains all the logic that's common to all the subtypes, right? And that's exactly the thing that we do here with Theorem of Sudoku. The Theorem of Sudoku actually captures information with it about all the base constraints that hold for every single Sudoku. So this thing has 81 constraints on the domain. Every single value in the 9 times 9 matrix needs to be between 1 and 9. And it contains the use of the distinct operator in Z3, where we say on the first row, column 1, column 2, column 3, all the way to 9 need to be distinct values. They can never be the same. And so all of those constraints end up in the base theorem. And then the thing that you express on top of that is the cells that you do know. Like in this case, you say, I know that the cell on row 1 and column 3 actually needs to be 2. This is really, you're sitting on the plane, you take your little book over there, you go to Sudoku and you just feed in, all those constraints. And of course, you could say, like, I know that cell 23, row 2 and 3 needs to be 5. Because that's what I see in the book here. And then ultimately, when you do solve on that thing, it will come back with, a finding for all of the cells, and that actually satisfies Sudoku rules. So that's the thing here. Now, it's interesting to see that currently this thing is emitting about an inefficient theorem for the Z3 to solve. But the fact that you see on a very high level allows the Sudoku type to optimize. It actually gets an expression tree that contains all of the information about Sudoku. Currently, it encodes it as natural numbers and uses, all this linear stuff to solve it. But it could actually find against more efficient ways in Z3 to do it, without you having to change the code. So you have this degree of separation or indirection by which, like, this mysterious Sudoku type can actually influence the way that the thing translates ultimately to Z3.
Yes.
So you have query providers, which in this case is linked to Z3. And on top of that, you have an extensibility model by which you can actually take an expression tree and rewrite it into a more efficient one. So you can do that, like, for example, for Sudokus. I have a sample of a place where there is a rewrite involved. And this is a kind of puzzle called a can-can. Can-can puzzles, I have actually domain-specific language here that I can parse to represent them as a string, just, to go totally crazy. But so this is really like how it would look on paper. So what does this mean?
Yes.
This means this is multiple cells here, right? So this is one cell over here. This is another cell over here. Actually, I also have it in Word somewhere. Let's actually see whether that still is on that place. That's the can-can puzzle. And so it says that the sum of the cells that are connected with small lines, this dotted line here, those two cells need to be 4. That means that, and they need to be distinct values as well. So possible solutions are this is 3 and this is 1.
Yes.
Or this is 3 and that's 1. It's commutative by default. Even for the minus case. Like in this case, the subtraction of those two cells needs to be 1. That means, well, this could be 4 and that could be 3, that could be 4 and that could be 3. Like, it's just the difference of those two cells needs to be 1. For multiplication and addition, of course, you can have more than 2 cells because they really commute. So this needs to be, the product needs to be 4. Well, that needs to be, 1, 1 and 4, 1, 2 and 2. Like, depends just, on the kind of Sudoku or can you actually have here. Well, the constraints are on the cells. This needs to be 24 and so forth. So you have this whole thing. But the interesting thing is that the constraints that you need to formulate to Z3 are basically much more elaborate than what you see on the diagram. And what you see on this diagram is like the sum of two things needs to be 4. That's fine, because sum is always commutative. But like this 1 minus thing, that's really an OR. It's like x minus y equals 1, or y minus x equals 1. Like, it's either of the combinations needs to both. So when you're formulating that theorem, you only want to state things that you do know, right? You want to say that the addition of cell 1 and then cell on row 1 and column 1 and cell on row 2 and column 1, that's those two cells over here, this and that. The sum needs to be 4. I don't care the majority. And so here you have those domain-specific, can domain-specific methods that actually translate into much more constraints for the solver and the read, because you have this, weird tools in this world. So you have a very compact way to state it, as opposed to in Z3, where you would actually have to state all the facts yourself. So actually, let's see whether this is this the can puzzle. This is Sudoku puzzle that's being solved here. The can is still working. And so this also shows that you could be much more efficient about this if you actually do much more extensive rewrites, knowing some of the Z3 C3 stuff that you can actually do. Like they have very efficient ways to do things with bit vectors, with arrays. So you have to pick your poison to solve it.
Yeah.
And picking that in this case is just, using the straightforward theorems that they provide.
Excellent.
So that thing will actually emit some complicated stuff. And then, there's a final one that I actually have sitting here.
Perfect.
That's a Kakuro puzzle. Don't know whether people know this particular thing. That's actually search for Kakuro. It's a Japanese kind of puzzle. It's a crossword puzzle for numbers. So actually, let's try to find one really quick. So yeah, here it is. It's actually kind of small. Let's try to get it a little bit bigger here. But so what you're seeing is it's a crossword puzzle that says the sum of those two things needs to be 16. So you have here is number 16, and it says that the sum of those two needs to be 16. The sum of those two needs to be, or those three needs to be 23, and so on. So it's actually typically you have the hint of the word sitting here, right? And that says horizontally, starting from this position, the word needs to be such and such. In this case, it's about sums. Now, in reality, what you're actually expressing here is that, the combination of those guys needs to be such that the sum is 20. But do you really want to specify, well, it's cell, let me see, cell on 4,2 and 4,3 and 4,4 and 4,5?
No, you don't.
Maybe you don't, right? What you want to express is all the things you know. And the white things you don't want to bother with. So you want to sort of say the things that you see on paper. You want to say, there is a black stone sitting over here. And now, if this thing says the sum needs to be 20 horizontally, basically the computer has enough information to figure out which sum needs to total 20. It can basically start iterating through the array till it finds a cell which is declared black. And so that's actually the thing that you do here. You formulate this puzzle as, cell 11 is black. Okay? Cell 12 over here, that's row 1, column 2, has a vertical sum which is equal to 23. I haven't set the cells that add up to 23. It will figure that out because at some point I will have something let's see, 1, 2, 3, 4, 5. 5,2, cell 52 will say that there is a horizontal sum of 24. That means that there is no empty cell over there because you have a constraint. So basically what this theorem solver does in this case, it will actually look at the topology of that whole puzzle and basically figure out what you mean. It will figure out that, in that case, 23 is really the sum of those three cells because it can't go any further than this cell. And so this basically shows that here we are capturing the expression trees of the entire theorem. And then what you can do at the point that you do solve, you can do optimization. And that's exactly the same thing as with LINQ to SQL, for example. LINQ to SQL could perfectly say, if you do get enumerator, we haven't gone to the database at all yet. We just have a whole expression tree and represent a query. Now, things I could do at that point is swapping around order by and where. Because doing the where before an order by is always more efficient. You first tossing out 99% of the telephone book, and then you're going to sort the remainder of people in the telephone book. Versus you're going to sort the whole telephone book, and then throwing out 99% of the things you spend so much resources on sorting.
Yes.
You have that expression tree, you can do all the rewrites that you desire before you go to talk to the external service to fetch the answer. In this case, it's exactly the same. In this case, you have some puzzle, you formulate it in terms of what you know, and then the puzzle has intrinsic knowledge of how it formulates the theorem for Z3 to actually find the solution for the puzzle. And so that translation step is very rich, meaning that the way you express your theorems can be very concise, very domain specific. And then the way they execute in something like Z3 can be very, complicated.
Sure.
That just the guy that wrote the Kakuro theorem needs to know about. He needs to know how to analyze a puzzle that you're feeding in. But the rest of the world doesn't need to know. And that's exactly the same with LINQ to SQL, right? if you do something like, do front clauses from V in products, from O and product.orders. Well, the fact that you do front clauses, that's very natural. But internally, that might result in a cross apply or join or, any kind of, take two tables and somehow combine the two. Like how that works on SQL, I don't know. Like, as the writer of that query, I don't need to know that. It's just a translation step. In this case, the translation steps can be very, very complicated.
Sure.
Which allows, very expressive, small and dense queries. And then, very rich results to come out.
Awesome.
And of course, you can see that in like bigger context as well. Like if you, at some point, we'll do LINQ to Solver Foundation as well.
Nice.
And there you will actually see that this whole query, which could be an optimization problem, where you want to, optimize the allocation of number of barrels of oil you get from two companies. Well, you could embed that whole query in a bigger query, which is an RX query, for example, that says like, whenever the price is changing in either of the two companies, I want to recompute this whole thing because now it might be more efficient to order the oil in a different way than it was yesterday. So essentially, then you have the same syntax for all of that stuff. Like you have a decision problem and a reactive query. Like you can sort of go between domains there. And
so that just reminded me of something. I've been thinking about the stock market a lot lately. And hey,
exactly.
reactive around Solver Foundation.
Yeah.
Beautiful.
Exactly.
That's how I'm going to pick my next stocks because,
okay.
I need to retire, man. And currently that's not going to happen.
I see. Yeah.
Right.
So, yes, I should actually use our technology.
I want to. The other thing I was thinking of as well is I'm going to take this down to Vegas because I could see some very interesting uses for Z3 in a gambling setting.
Okay.
Just kidding, casino owners.
Yes.
That's why Bart's not allowed in Vegas, by the way.
Yes.
Man.
Well, I have some, Z3 long shift down here, and so I would actually see the table and immediately solve the constraints. Yes.
Right on, man.
Yeah.
Hey, it's always great to talk to you, Bart.
Okay. Thank you.
Just keep on keeping on, man. If you're doing LINQ to everything,
Yes.
because you're making the dream real.
Yep. We own it.
We will talk to you soon.
Okay.
Take care, buddy.